Hello everyone, welcome to lecture 32 of the online course on modern display technologies, flat panel display. Today's lecture will be on bistable ferroelectric LCDs and their driving schemes. So here is the lecture outline. We'll talk about the multiplexing problem in passive matrices and the motivation. Okay. We'll talk about the three routes to multiplexed passive matrix displays. Then focus on why bistability is needed, and that could be the third route to multiplexibility. And then we'll look into the surface stabilized ferroelectric liquid crystals, their structure and the optical properties, and look into the switching dynamics, that is the voltage time area law. After that, the focus will be on the passive matrix drive scheme, and then we will establish a bridge to the bistable pneumatic displays, which will be covered in the next lecture. So, why passive matrices run out? So, we will actually talk about multiplexing problem in the passive matrix. So, we have seen that in a passive matrix there is no switch at the pixel level. So, a pixel is basically addressed by driving its row and its column simultaneously, which means every pixel sharing that row or that column basically receives the same voltage. Okay. So, the pixel we want carries the select voltage, however, the neighbors also carry a non-select voltage that is smaller, however, it is not 0. So, what happens when we have more rows? That means a smaller margin is left between on and off, and the contrast basically collapses once the row count grows. So, that basically is the limit is there, which is set by the steepness of the voltage transmittance curve. So, the motivation here is to solve this problem, that we require steep voltage transmittance curve that could enable the passive STN addressing. Okay. So, you can actually go for active matrix, which is basically incorporate one TFT switch per pixel. The other could be like you think of bistable materials, where the pixel basically remembers its own state. Now, what is the benefit of bistability? It basically removes both the transistor and the refresh requirement. So, here we will look into the three routes to multiplex displays. Now, the first point is why multiplexibility is hard. First thing is, a passive matrix has only rows and columns. Okay. So, whatever selects a pixel must basically come from the combination of that row and the column voltage, right. So, there is no switch sitting at each pixel level, that we understood. So, one route is that engineer a steep voltage transmittance curve. So, in that case, what will happen, if the curve is steep, a small RMS voltage difference between the selected and the non-selected pixels will be enough to separate the on from the off state, right. The second route could be, as I already mentioned, that you can add a active matrix. That means you install a TFT, thin film transistor, at each pixel. That basically gives every pixel its own independently controlled voltage. And the third route, that is the today's subject, that is the theme for this entire module, that can we make the liquid crystal material itself bistable, so it basically can hold its state with zero applied field. And this bistable pixel will remember its last written state indefinitely. That means you will not require to refresh every 16.7 millisecond, okay, that typically a pneumatic liquid crystal display requires. So, what does this bistability buy us? First thing is the zero field memory. That means once switched, the liquid crystal director configuration is mechanically and electrically stable with no holding voltage at all. And then there will be no fundamental limit on the number of the multiplexed rows, and that will be ideal for very high information content passive displays, something like e-paper or large signage, okay, or low power indicators. However, this bistability also brings some trade off. So, most bistable liquid crystals basically offer only two discrete optical states. So, the smooth gray level or the gray scale, that is difficult in this kind of display. So, this is something that will be discussed through and through in this particular module. So, what are the bistable display technologies or liquid crystal technologies that are used in practice? The first one is the ferroelectric, then pneumatic, and then the cholesteric reflective display. So, today this bistable ferroelectric LCDs, that is BFLCs, okay, built from the surface stabilized ferroelectric liquid crystals or SSFLCs, okay. These are historically the earliest bistable liquid crystal display technology that was found out by the researchers. Now, let us briefly look into this surface stabilized ferroelectric liquid crystal and how it looks, okay, or how it behaves. So, this SSFLC devices are already familiar from the previous lectures, we have already discussed them, but today here we will look specifically at how that bistability is basically exploited to build and drive a multiplexed display. Okay. So, here you see the schematic of a SSFLC display director configuration. So, in the first figure, this one, the director is basically along the direction A1, okay, as you can see here, when the field is applied up, okay. In the second case, the field is applied down and the director positions are now along A2, okay, this is the field, here is the field, okay. So, this is the polarizer, this is the analyzer, and this is your liquid crystal cell, okay. So, you can see the cone axis also here. So, these are the two cases, and this is where the positions are basically shown. In one case, you have this theta along this axis, okay. In other case, the theta is on the other side. So, because it is like this and this, so it's like plus and minus theta. So, you can see from here how they are moving, okay. So, what is this cell? You can actually see that it is basically built from a chiral smectic C-star liquid crystal, and these are basically surface stabilized between two closely spaced substrates, so that its natural helical twist is basically suppressed. So, when we say too stable, okay, that means there are two basically stable states, okay, and these are typically possible because of getting purely planar director configuration which exists when there is no field, okay. So, you can call them as state 1 and state 2, okay. So, because the entrance polarizer you can see here is set parallel to state 1, okay. So, this is why you can see that the state 1 will be called the dark state, okay. And the cell is placed between the crossed polarizer, and when you put the, as I mentioned, when you put the entrance polarizer aligned parallel to the state 1 director, okay, you will get basically dark state because this analyzer will block the light, okay. So, that is why this by construction this state 1 is the dark state and the transmittance is exactly 0. Now, when you switch to the state 2, okay, where the liquid crystal director has basically rotated by a cone angle of 2 theta, okay. So, earlier it was here, now it is going to this direction, okay. So, the movement is around 2 theta, and that is where the transmittance can be seen through the analyzer, okay. So, 2 theta is basically the cone angle that is swept by the director when the material switches from state 1 to state 2. And we have already seen that the state 1 gives you 0 transmittance by construction, and state 2 gives you a transmittance value which can be given as T equals sin square 4 theta into sin square pi delta n h by lambda. Now, this term delta n h is basically the retardation from the cell, okay. So, it is basically the product of the liquid crystals own birefringence and then the cell gap, and the lambda is basically the wavelength of the incident light. Now, how to do the optimum design in this case? You can choose 2 theta to be 45 degree and if you consider this factor to be 90 degree, that is pi delta n h by lambda to be 90 degree, you will see that both of these terms are basically maximized, they are both giving 1 1, and you get the maximum transmission. So, under these ideal conditions, you can see that the state 2 will reach near unity transmittance, while your state 1 is remaining perfectly dark. So, you get very good or very high on off contrast ratio, which is purely set by the molecular geometry and the design of the cell. Now, how does the switching between the two states happen? So, you have already seen that this SS FLC states are basically addressed by the polarity of an applied DC voltage pulse, and it does not actually simply by its magnitude. So, when you have the positive polarity pulse driving the liquid crystal, so you can go into state 1, and once the pulse ends, the state basically stays there. Then you can actually if you want to go to state 2, you need to drive this with a negative polarity pulse. So, that will basically drive into state 2, and it can remain there after the pulse is removed. So, this is basically a polarity based switching, not the amplitude based switching, okay, and this is fundamentally different from the ordinary pneumatic liquid crystal displays, where you will see the transmittance basically tracks the RMS voltage continuously. However, here it is basically based on the polarity. So, the ferroelectric liquid crystals with high spontaneous polarization will respond cumulatively to a pulse rather than instantaneously, and that will basically directly lead to this kind of concept of voltage, time and area, which is shown here. Okay. So, this is the concept of voltage, time, area. Okay. So, here you can see that the voltage, time, area A is important as the time integral of the applied voltage waveform, which is analogous to impulse in mechanics. So, you are basically having the force integrated over time rather than the force itself. Okay. Now, why an integral quantity makes physical sense here is that you will see that what we are doing, this FLC switching is basically governed by the accumulated voltage, time, area A of the applied pulse. Okay. So, it does not only depend on the peak value itself or the peak voltage itself, and A, as you see, is basically time integral of the applied voltage over the integral of the pulse, say T1 from T2, right. Now, why this integral makes sense? The switching process basically involves the ferroelectric polarization accumulating torque on the director over the duration of the pulse. So, both the pulse height and the width will matter jointly, not separately, right. So, that is why you will see that the two threshold, one is called ATH, which is basically the onset of switching, and another is AS, which is basically the completion of switching. Okay. So, these are the two thresholds which are getting involved in this, and in this particular figure where you are plotting the transmittance versus the voltage, time, area, you finally see a S shape curved with two knees. Okay. And here you can basically see that below ATH there is no change of state, and above AS the liquid crystal is fully committed to the new state, and between them you can basically see a gray kind of transition for this case as well as also this case. So, how to read this transmittance area curve? Okay. So, you can start with the liquid crystal in state 1 where the transmittance is very low, okay, say at T1 level, that is almost 0. Now, as the positive voltage, time, area increases past your ATH, so when you go here, the transmittance basically begins rising towards T2, okay, and as soon as A basically approaches AS or it exceeds AS, the liquid crystal is now completely switched. So, your transmittance basically saturates at this maximum value of T2. Now, when you reverse the pulse, what happens? when you reverse the polarity of the pulse and make A to be negative, okay, that means in this side, you will see that below minus ATH, the reverse transition happens, okay. So it is starting to come down, and below this minus ATH, the liquid crystal has completely returned to the state T1. Okay. So the window that you see between the ATH and the AS is in principle the partial or the grayscale kind of intermediate transmittance level is happening basically here. Okay. Now, how do you design a passive matrix driving scheme? Okay. So the goal here is to address every row of an SSFLC matrix using only shared row and column waveforms, exploiting this voltage time area switching law. Okay. So each frame basically begins with a reset. So here you can see the column voltage, the row voltage, the pixel voltage, and also the resultant transmittance. So you basically start with a reset, and this is where a positive and then a negative voltage is applied across all rows simultaneously. So this is how the row voltage is changing. So that basically forces every pixel to a dark state. The row basically currently being addressed will also receive a opposite order pulse. This is the one during its turn in the particular frame. So after then your column voltage is also set to positive negative or positive to negative basically. Okay. So here you can see that happening. So the column voltage is set to Pn to select the bright state for that particular pixel, or you can go for N to P, okay, to keep it dark, right. And the rows which are not currently being addressed will be simply held at 0. So this is the overall time frame, okay, over which the whole thing is working. So for the remaining part, you can see that the pixels are left undisturbed. So what you understand that you have in phase row and the column area, when it exceeds AS, that basically gives you the bright state. Okay. So just by looking into this picture also, you can understand that a global reset will basically first force all the rows to dark state, followed by a row by row selection process or phase, which is the standard structure for most bistable liquid crystal passive matrix scheme. Now there are basically 4 voltage combinations which are being used. One is you can see the reset pulse to all rows, which is already shown here. The second one is basically NP pulse, that's like negative to positive pulse, okay, to the addressed row, and then you can have PN or NP to the column row, okay, it's actually this one, column row is this one, okay, and then based on like this PN or NP column voltages, depending on whether the pixel should end up being bright or dark, okay, and if you want to, and you just want to make sure that all other rows are getting zeros, okay. So this is how it looks like. So the out of phase combination will stay below ATH, that means it will give you dark state. So here you can see these are the bright states and these are the dark states. Now why this scheme avoids crosstalk? You can see that addressed row and the column voltage PN. So the second half of the resulting pixel pulse basically pushes the voltage time area above AS. So your bright state is basically getting selected. Now the addressed row, for them the column voltage, if it is NP, in that case the pixel's second half area will stay below ATH. In that case the dark state is basically retained. Now for all non-addressed rows which are held at 0 volt, in this case their pixels will see a time voltage time area that stays between minus ATH and plus ATH, so that the state is preserved and there is no unwanted switching. So, this inequality, that means keeping each unselected pixel's accumulated area inside this plus minus ATH, this is how the crosstalk is basically prevented in every bistable FLC driving scheme, and this condition should be satisfied to ensure there is no crosstalk. So, no, or you can say non-addressed pixels never switch mid-frame. So, same argument can be reapplied row by row across the frame, and what you get is basically a genuinely passive matrix bistable display. Now, keeping the liquid crystal in DC balance, okay, that is important because this is the physical mechanism of ionic DC bias. So, even trace mobile ionic impurities in the liquid crystal mixture. So, the liquid crystal reorientation dynamics basically depend on the square of the electric field. So, switching speed itself does not care about the polarity. However, a sustained one-sided, that means a net DC bias, slowly sweeps the ions toward the alignment layer interface, where they can basically form a thin charge layer, and that charge layer shields the true liquid crystal voltage. So, what will happen? The pixel's actual driving voltage becomes misinterpreted over time, seen as a grayscale or a threshold drift. So, how to fix this problem? You can think of alternating the polarity of successive addressing pulses. That means you are basically going for a AC drive scheme other than the DC one, and you can use a high resistive liquid crystal mixture that can slow the ion migration. So, this DC balancing principle will reappear for every liquid crystal drive scheme, whether it is bistable or not. So, let us compare this SSFLC with other multiplexing routes. So, the steep voltage transmittance curve, so there curve STN, so there you can see that it needs no bistability at all, but the contrast is quite sensitive to the viewing angle and to the temperature. So, when you go for active matrix, that is TFT LCDs, okay, so they basically give excellent grayscale and allow fast switching, but a transistor must also be fabricated within every pixel. So, that is costly for very large area and also for very low cost passive style panels. Okay. So, this is why our bistable FLCs, that is the SSFLC that we are considering here, they show genuine zero field memory and they are very fast. They typically work in the microsecond range switching. However, they have some problem of the limited native grayscale and mechanical shock sensitivity in every panel design. Otherwise, they are good, right? So, in practice, SSFLC found strong niches in micro displays, some professional and industrial application, while you will see the high volume consumer LCD manufacturing has basically moved towards the active matrix pneumatic technology. Now, what are the key equations of bistable ferroelectric LCDs? So, we have already seen this equation. The transmittance is T equals sin square 4 theta into sin square pi delta n h by lambda. So, you can calculate the A, that is the area, which is the voltage time area of the addressing pulse, which is given by integration over time from T1 to T2 for Vt dt. Okay, and the switching happens when modulus of A is greater than ATH partial, and also when this is greater than the AS. So, we know all of these variables here. Theta is basically the half cone angle swept between the state 1 and state 2, okay, and delta n is the birefringence, h is the cell gap, lambda is the wavelength of light, A I already mentioned, that is the voltage time area of the addressing pulse. So, that is basically giving the time integral of Vt, and these are basically the partial switching and the complete switching thresholds of the voltage time area curve. Now, this SSFLCs basically achieves bistability through the layered schematic Sikdar structure and its two surface stabilized tilt states. So, what is the next family, that is bistable pneumatic liquid crystal displays. Okay. So, this is where this family instead engineers the bistability through a different path, that is through the hydrodynamic flow or surface anchoring effects. So, here no schematic layering is basically required. So, 5 pneumatic bistable variants which are typically used in practice are these ones: twisted, untwisted, that is BTN, then zenithal bistable, surface induced, mechanically bistable and bistable STN. Okay. So, the advantage these have over SSFLC is that they are simpler, far more common pneumatic materials are used and the processing is easy. However, they have some shared drawback that they usually still have no native grayscale. So, we will basically in the next lecture begin with this twisted, untwisted bistable pneumatic, that is the BTN display. Sometimes they are also called the 2-pi bistable display, where you will see that the two states basically differ in a twist angle by exactly 2 pi. So, to summarize, in this lecture we have seen that bistability is basically the third route to multiplex this passive matrix displays alongside the steep VTSTN and the active matrix TFTs. We have also seen that SSFLCs stores information in two stable planar director orientation, which are selected by the polarity of the DC pulse. Now, the switching basically obeys a voltage time area law. It does not obey an instantaneous voltage law. So, it basically depends on both the pulse height and the pulse width. Okay. And a reset then address kind of driving scheme using positive negative or negative positive row and column voltages can address a full passive matrix while completely avoiding the crosstalk. And with this, in the next lecture we will move on to studying the bistable pneumatic LCDs as an alternative to this SSFLCs, and then where we will begin with the twisted untwisted BTN displays. So, with that we conclude this lecture. If you have got any query, you can drop an email to this email address mentioned in the course name and the lecture number on the subject line. Thank you.